Welcome to the deep dive. Today we're plunging into one of the most consequential, yet I think least understood shifts happening in the AI industry right now.
Yeah, it's a big one.
We are moving well beyond the standard headlines about, model capability, the what of AI, and focusing entirely on the underlying infrastructure. We're talking about the how and the where that intelligence is actually powered in the real world.
Exactly. It's about speed, it's about scale, and it's about a company that is, well, really a dark horse, and they're fundamentally challenging the entire established order of AI compute.
That's right. Our deep dive is based on a really extensive stack of material, and it all centers on Groq's CEO, Jonathan Ross. He is a genuinely fascinating figure.
He really is. I mean, his pedigree is impeccable, but it's also completely unconventional. He started his career designing Google's foundational processing unit, the TPU.
And now he's aiming to fundamentally reshape how AI is deployed globally, directly challenging these, multi-billion-dollar incumbents like Nvidia.
So our mission today is to really dissect this challenge. We're going to uncover the technical architectural decisions, the strategic market timing, and even some of the unique cultural choices that built this challenger company.
And as you listen, you should keep one distinction in mind, because this is key. This isn't just a story about a fast chip. It's about the seismic shift from training massive AI models.
Those where the industry started,
Right.
and where, massive parallel GPUs are just king.
To running them efficiently, which is a domain known as inference.
And that pivot from training to inference
Yeah.
is, well, it's everything. As AI moves out of the lab and gets integrated into every single application you use, speed and cost just become the entire competitive battlefield.
They stop being secondary factors.
Exactly. The demand for real-time generation, what we call ultra-low latency, is creating a completely new architectural war. And, the winner of this inference war is going to define the next decade of AI deployment.
So we're going to begin by uncovering the almost mythical origin story of Jonathan Ross, but then pivot quickly into the surprising technical solution he championed.
We're going to get into how an innovative design that was thought to be lost to history, the systolic array, helped solve a multi-billion-dollar problem.
And crucially, how Groq's singular focus on the compiler, the software layer, became its ultimate competitive moat. It allowed them to scale where everyone else is just bottlenecked.
What's truly fascinating here is how constraints, not having the resources or even not having the ingrained traditional knowledge, led directly to breakthroughs. It's a powerful story.
Okay, let's unpack this entire picture, starting with an origin story that really defies the typical Silicon Valley playbook.
It really does.
Jonathan Ross's journey, it's one of the most unique we've ever come across. And it's so important to understand this background because it fundamentally shaped his non-traditional approach to architecture.
Yeah, I mean, when you look at successful tech founders, you usually see this very predictable pattern, right? Elite universities, specialized degrees, all that.
Ross just completely bypasses that entire structure.
He does. And the detail that just immediately stands out is that he is a high school dropout.
Right. Which is rare enough for any founder, but for someone who went on to architect one of the most important pieces of AI hardware ever created, it's almost unheard of.
But that lack of, traditional certification, it gave him a kind of radical freedom.
So how did he get his start? He got a job as a programmer.
Yeah, he got a job as a programmer, and this is where he found some, let's call it unconventional mentorship. His boss saw his raw talent and actually encouraged him to attend Hunter College.
But he went unmatriculated, right? He wasn't officially enrolled.
Exactly. He wasn't pursuing a degree. He was just taking classes because he was curious and, smart enough to handle the material.
And this habit of just seeking knowledge without following the official path, that continued.
It did. He later transferred to NYU, and instead of just, completing a standard undergrad degree, he immediately started taking PhD courses while he was technically still an undergrad.
Wow.
The intellectual horsepower was clearly there, but the formal structure just wasn't. And today, he still doesn't have a high school diploma or an undergraduate degree.
No high school diploma, no undergrad degree, and yet he designs these era-defining billion-dollar chips. It's an incredible validation of talent over credentialism.
And this background is just so influential. I mean, it suggests that not knowing the traditional constraints, not being taught the right way to do things, can lead you directly to these counterintuitive solutions that incumbents would just dismiss.
So how does an uncredentialed engineer like that end up at a place like Google working on what became, the most pressing technical problem of the era?
Well, his entry was actually a direct result of those connections he made at NYU. Someone he was taking PhD courses with recognized him at a Google event and referred him.
So the network still mattered, even without the degree.
The network and the intellectual camaraderie, yes, maybe more so. When he first got there, though, he wasn't on AI. He started on Google Ads.
Which sounds kind of mundane, but the engineering challenge there was actually immense.
Oh, yeah. He wasn't just working on the production system. He was building these giant, high-stakes test systems to rigorously check the production environment. The sources say this was actually harder than the production system itself.
And then came the famous Google 20% time, but he even did that his own way.
He did. He called his extra work MCI time, which is a deep-cut reference to old phone company ads about free nights and weekends.
So this wasn't during his work time.
No, he was going up every single night and working with the speech team on this secret side project on his own time. And that commitment is what led directly to the concept that became the TPU, the Tensor Processing Unit.
And the birth of the TPU itself was almost an accident, right? It was not a priority project.
Not at all. It was funded out of a VP's leftover money, a slush fund. It was never expected to succeed.
And that lack of expectation was the key.
It was the most critical factor. It gave them the cover they needed to be truly radical, truly unconventional. If it failed, nobody would care. But if you're a high-profile project, that fear of failure, it can just kill innovation before it even starts.
Which sets the stage perfectly for the problem they had to solve. And it wasn't just a technical problem, it was a genuine existential financial threat to Google.
Yeah, let's talk about that moment, because everything changed for Google and for AI compute right then. The crisis hit in 2012. For the very first time, a machine learning model for speech transcription actually outperformed human beings.
Which, on the surface, sounds like a huge success, an amazing win.
It was a technological triumph, but a financial catastrophe. They called it the success disaster. The model worked, the tech was world-changing, but implementing it globally would require an unbelievable amount of compute.
And Jeff Dean had that famous presentation that laid it all out.
2 slides that basically define the history of inference. The first slide, good news, machine learning works.
And the second slide was the nightmare.
Bad news, we can't afford it. The price tag to roll out speech recognition globally would mean doubling or even tripling Google's entire global data center footprint.
We're talking billions of dollars here.
$20 to $40 billion.
Yeah.
And that was just for speech recognition. Not search, not ads, nothing else. It was completely uneconomical.
So that became the core lesson of inference. Training is expensive, but putting a model into production at scale is just, it's a different world.
It's exponentially more expensive. The demand just explodes like 10x, 20x overnight. They needed a massive, massive reduction in the cost and energy required to run these things.
So if that's the multi-billion-dollar problem, what was the specific technical nut they had to crack?
Well, Jeff Dean pointed out that the one algorithm eating up most of the CPU cycles was matrix multiply, the core math of deep learning. So the insight was, let's stop trying to make general-purpose chips better. Let's build a massive, dedicated matrix multiplication engine.
But Ross's team wasn't the only one working on this. There was internal competition.
Oh, fierce competition. 2 other teams were taking more traditional approaches. One of them was even led by a Turing Award winner, a legend in the field.
So the smart money was on the established expert.
Absolutely. And yet, it was the small, underfunded team led by Ross, the high school dropout, that came up with the winning architecture.
The systolic array.
The systolic array. And the irony is just immense. The Turing Award winner later said that whoever came up with it must be really old, because that idea had fallen out of favor decades ago. It was considered obsolete.
So why was it obsolete? What was the issue?
Well, systolic arrays are inherently rigid. They're built for one-task, massive matrix multiplication, and they require data to flow in this highly deterministic, ordered way.
So they're terrible for general-purpose computing.
Exactly. GPUs and CPUs won the previous wars because they were flexible. But when AI came along, the main bottleneck became that one single, massive, rigid calculation.
So the very thing that made it obsolete made it perfect for this new problem.
Precisely. And Ross, because he didn't have that traditional training, he didn't even know the academic terminology. He just said it was the obvious way to do it.
The lesson there is just so powerful. If you come at a problem knowing all the right ways to solve it, you might be blind. Not knowing the rules gave them the edge.
It's the hallmark of innovation, driven by first principles.
So the TPU scales up, it solves this $40 billion problem, and then Jonathan Ross just walks away. Why leave right at the peak of that success?
It really goes back to the political gravity of big companies. He said that when a project gets that successful, senior people just want to own it. The bureaucracy starts to constrain your ability to actually build and iterate.
So he moved on to Google X, the rapid evaluation team, looking for that freedom again.
He did, but he found he was mostly playing around, as he put it. Lots of cool ideas, but nothing ever turned into a real deployed production system. And that's what motivated him. He wanted to take something from concept to production, start to finish one more time.
And that desire led him to the idea for Groq around 2016, which was driven by this crucial insight he had about the market, the open source realization.
That's the pivot. He was thinking about building a better image classifier, but he quickly realized the business wasn't in the software.
Why not?
He saw that all the foundational software, TensorFlow, the models, the frameworks, it was all being given away for free. It was obvious that AI was going to be overwhelmingly open source.
And you can't build a defensible, high-margin business on free software.
Right, it would just be hard scrabble.
Why?
A constant fight. So he pivoted to hardware, realizing it offered this unique, slow-moving advantage, the hardware mode.
So the idea is that atoms are just slower to copy than bits.
Basically, yeah. Building a chip takes so long, at least 4 years, that if you launch something truly innovative, competitors are years behind just trying to copy you. It gives you this huge temporal advantage.
And this all coincided with the TPU paper finally being published, putting Ross's name on the map.
It did. And he was shocked that Google was building its own hardware. He realized they must know something the rest of the world didn't, which was the scale of the inference problem. He decided the rest of the world needed access to that capability. And that was the start of Groq.
The investment story around Groq's founding is pretty legendary now.
It is. A VC was so impressed they wrote a check before the company was even incorporated. Ross had to literally form the company after the check was written.
The investor called it either complete stupidity or something that would look like genius in 20 years.
It shows the belief in Ross's talent. But here's where the Groq design gets really interesting. They weren't 100% committed to hardware at first. They knew the real problem was software usability.
Because of his experience programming the TPUs at Google.
Right. At Google, every team needed a dedicated person just to hand-optimize models for the hardware. Ross called it absolutely crazy, fundamentally unscalable.
And they found out this wasn't just a Google problem. Nvidia had the same issue.
They hired people from Nvidia who confirmed it. The whole GPU architecture relies on these low-level CUDA kernels, basically requiring assembly-writing hackers to get performance. You just can't scale that.
So Groq's core innovation wasn't actually the chip, it was the software that manages the chip.
Exactly. They focused entirely on the compiler for the first 6 months. They famously banned whiteboards because people kept trying to draw chips instead of focusing on the software stack.
And the result is what they call a kernel-free approach. Okay, for those of us who aren't compiler engineers, what is a kernel here and why is getting rid of it such a big deal?
So a kernel on a GPU is a small program that tells the parallel processors exactly how to handle data. It's complex scheduling. You need a human expert to write one for every single model.
Which is why it's so slow when a new model comes out every 2 weeks.
Correct. Groq's design, because it's built on that rigid, deterministic systolic array, means the timing and data flow are perfectly predictable. The compiler can handle everything automatically. It eliminates the need for that whole layer of expert human optimization.
So that deterministic execution is what solves the scalability problem. You don't need an army of hackers.
You don't, and that brings us right to the core technical battlefield.
Right. Groq is the challenger. Nvidia is the champion. We need to really define why Groq can succeed here. Let's restate that fundamental difference between training and inference.
This is the essential distinction. Training is about raw throughput, measured in tokens per month. It doesn't matter if a single batch takes 1 second or 100 seconds. Nvidia is the undisputed king of training.
But inference, Groq's focus, is a totally different game.
Totally different. It's measured in milliseconds. It's the immediate real-time response for the user. When you ask a chatbot a question, that's inference. And if you're waiting 3 to 5 seconds, you've already lost the user.
And the market is already shifting hard in that direction.
It is. Nvidia's own earnings show the market is already 40% inference. And Ross predicts it'll settle at 90% to 95% inference.
That presents a classic textbook innovator's dilemma for Nvidia, doesn't it? If inference is the future, why can't the market leader just pivot and win?
Because winning at low latency inference requires them to sacrifice everything that made them successful in training.
They have to throw away the entire architecture.
The entire stack, the chip, the networking, the system, the runtime, the compiler, the orchestration, all 6 foundational elements, they'd have to give up their incredibly profitable training business to chase this new, high-volume, potentially lower-margin market.
They're trapped by their own success, basically.
It's an innovator's dilemma on steroids. And we can see why they need to make that shift by looking at the user data. That latency really matters.
How much does it matter, really?
It's everything, economically. Delivering an experience under 250 to 300 milliseconds maximizes revenue and engagement. And the hard data is just stunning. Every 100 milliseconds slower leads to 8% less engagement on desktop and a massive 34% less on mobile.
A third of your mobile users gone for a tenth of a second of lag. That's a death sentence for an app.
It is. And it explains why low-latency inference is the future. If your AI is slow, your application dies.
So let's turn to the technology that lets Groq achieve this. Their chip is the LPU, the language processing unit. How is it fundamentally different from a GPU?
Well, a GPU is designed for massive parallel tasks, like rendering a 3D scene. The LPU is designed to do things in parallel and sequentially, with a huge emphasis on extremely fast iteration.
And why is that sequential part so important for language models? I thought it was all just big parallel math.
The math is parallel, but the generation of text is inherently sequential. The model generates the first word, and that word feeds back in to change the probabilities for the second word, and so on. It's a rapid, iterative loop.
So it can't know the 100th word without knowing the 99th.
Exactly. Just like AlphaGo couldn't pick its 30th move until the 29th was chosen. So the ability to process those sequential steps with very, very low latency is key to both the speed and the quality of the output.
And this is something we can actually leverage as users.
Yeah, you can. Ask an LLM to generate something, then immediately ask it, what are 3 ways you can make your answer better? Now apply that. The LPU's architecture is built to handle that kind of rapid, sequential iteration incredibly fast.
But Ross knew that being a little bit better wasn't enough. He had this 10x performance mandate.
Absolutely. In the chip world, 15% better is an amazing win. But he knew that wouldn't be enough to convince customers to switch to a whole new architecture. They needed to be 5 to 10 times better.
And to get there, they had to make some really radical choices, specifically avoiding the components that constrain Nvidia.
That's the brilliance of the strategy. They stopped using the bleeding edge, supply-constrained parts. They used older 14-nanometer tech, older interconnects, and most crucially, they stopped using external memory.
Okay, explain the impact of ditching external memory. That sounds huge.
It's everything. Think of a GPU as a factory that constantly has to stop production to get parts from an off-site warehouse. That warehouse is the external memory, specifically high bandwidth memory or HBM.
And going to that warehouse costs time and energy.
A tremendous amount of energy. A huge chunk of a GPU's power budget is just moving data back and forth. Groq's design puts all the memory right on the chip with the processors. It's one giant, continuous assembly line, no more trips to the warehouse.
So by being architecturally different, or orthogonal, they also sidestepped the supply chain battle.
Precisely. Nvidia has locked up the entire supply chain for HBM, for the special connectors called interposers, for the high-speed cables. If you want to compete using the same parts, you're looking at a 2-year lead time.
But Groq doesn't need any of those parts.
Nope. And that turns manufacturing speed into a massive competitive edge. While a GPU order takes 2 years, Groq can deliver the first parts of a 1 million LPU order in 6 months because the parts are readily available from multiple sources.
Which brings us to the economics of all this. The rubber meets the road.
Right. Groq measures 2 things: tokens per second per user, which is the user experience, and tokens per dollar, which is cost efficiency.
Okay, so give me the hard numbers. How much faster are we talking?
It's pretty startling. On a large 180 billion parameter model, Groq's current chip runs at about 200 tokens per second. NVIDIA's next generation, B200, it runs at less than 50.
Wait, so Groq's current generation is 4 times faster than NVIDIA's next generation on that key user experience metric?
That's what the data suggests?
Yeah.
And the cost comparison is maybe even more staggering. Groq's is about 1/10 the cost per token versus a modern GPU.
That's a game changer. For the last decade, half of every VC dollar went back to the hyperscalers for ads or compute. AI promises to change that, but only if compute is cheap.
Exactly. If inference is astronomically expensive, then AI just becomes another way to funnel money back to the hardware monopoly.
Speaking of which, NVIDIA announced the B200 with this huge claim of a 30x performance increase. How do we square that with the numbers you just gave?
Well, you have to look at what they're measuring. Ross mentioned that NVIDIA engineers actually contacted him, sort of embarrassed by that 30x claim, saying it hurt their credibility.
So it's marketing spin.
It's almost certainly measuring training throughput or some synthetic benchmark. I mean, if you take their claimed 50 tokens per second on the B200 and you divide it by 30, it means the previous generation was doing less than 2 tokens per second.
Which is unusable. No one would use a chatbot that slow.
It's impossibly slow. So the 30x claim is pretty meaningless for real-world inference. And this all comes back to flexibility and speed to market.
Right, a new state-of-the-art model comes out every 2 weeks.
And if you're reliant on handwriting CUDA kernels, you just can't keep up. We have examples of this. When Llama 2 launched, AMD took about a week to get it running efficiently. Groq had it running in 2 days.
Because the compiler just handles it.
The compiler handles it. The latest example is the Kimi model, a trillion-parameter model. It launched on a Friday. Groq had it in production by Monday, and it took them 24 hours just to download the file.
So they compiled it faster than they could download it.
Exactly. That speed to market is critical, especially now that model quality is starting to bunch up. When GPT-4 and Anthropic and Mistral are all in the same ballpark on quality, the differentiator becomes cost and speed.
Which brings us to the non-technical side of Groq. The culture, the strategy, their plan for global expansion. First, team building. How do you hire in this crazy market?
It's incredibly hard with these multi-million-dollar pay packages for AI researchers. But Ross's philosophy flips that on its head.
He says don't chase the young AI researchers.
He says hire the best, most grizzled engineers who know how to ship stuff. His reasoning is that those seasoned engineers can learn AI faster than an AI researcher can gain 20 years of production deployment experience. That experience is the scarcest asset.
And this ties into his leadership philosophy, intentional leadership.
Yes, from the book, Turn the Ship Around. It's the opposite of command and control. The leader states the objective, and the team members take ownership to achieve it. And critically, they speak up if they see a problem.
The submarine analogy.
Exactly. The captain says, dive the boat. The officer says, diving to 500 feet. But if the engineer knows a hatch is open, they yell, stop it, the hatch is open. That distributed accountability prevents catastrophic errors.
And they made this tangible with the goal coin.
Every employee carries a coin with the goal. 25 million tokens per second. A simple, clear, measurable goal that aligns everyone. He said there are already over 20 million, so they'll have to retire the coin soon.
Groq's culture was also forged by intense financial scarcity.
Yes, Ross calls having too much money financial diabetes. He says constraints breed innovation. And for most of its history, Groq was the most poorly funded AI chip startup. At one point, they were 3 weeks from running out of money.
A near-death experience for the company.
It was. They couldn't do layoffs, but a full pay cut felt unfair. So they came up with this creative solution, the Groq bonds.
Based on WWII war bonds.
Exactly. Employees could voluntarily reduce their salary in exchange for equity. And the response was just astounding. 80% of employees volunteered, and half of them reduced their salary to the legal minimum.
That saved the company and built this incredible level of trust.
It did. And that culture of speed and commitment now dictates their global expansion. Their motto is, build fast.
And their deployment speeds are just unheard of.
They deployed a data center in Saudi Arabia in 51 days. Then they beat that in Finland, deploying one in just 34 days.
How is that even possible when the lead time for these things is usually years?
It's the architectural choices paying off. They partner with people who can move fast, and they use existing infrastructure. In Finland, they just rented an old air-cooled facility that hyperscalers were leaving. Because the LPUs are air-cooled, they don't need to build new, specialized liquid-cooled data centers, which takes years.
And the scale they're aiming for is just audacious.
It's staggering. Meta is aiming for 650,000 H100 equivalents by the end of the year. Groq plans to deploy 100,000 of their faster LPUs this year, but by the end of next year, they plan to deploy 1.5 million LPUs.
For context, how many H100s did NVIDIA even ship last year total?
About 500,000.
So Groq's plan to deploy 1.5 million LPUs. I mean, the implication is that they will likely have more dedicated generative AI inference capacity than all the hyperscalers combined.
You're saying they could capture roughly half of the world's inference compute capacity in a single year?
That's the implication. It would fundamentally reset the speed and cost of AI globally. And developers are noticing. They have 2 million developers in their ecosystem, and 400,000 of them are in India with zero marketing there.
So we've seen how focusing on speed and cost has opened up this new front in the AI revolution. It's a crucial shift for every company building AI applications.
It truly is. And the final thought Ross offered when asked about the future of AI, it was really profound. He compared large language models to Galileo's telescope.
The telescope that proved we weren't the center of the universe.
Right. Just as the telescope showed us the physical universe was far larger than we thought, LLMs are a telescope for the mind. They're showing us that the universe of intelligence is just. It's more vast and complex than we ever imagined. And that realization can feel a little scary at first.
It can. But Ross believes that over time we'll realize how beautiful that universe of intelligence is, and we'll find our place in it. We won't be afraid of it.
So the mission isn't just about selling chips. It's about reducing the friction, the latency and costs that prevents us from using this new telescope.
Precisely. If intelligence is going to be a utility, it has to be cheap, fast, and available everywhere. That's the scale they're trying to enable.
That's a powerful and deeply philosophical thought to leave with. The architectural shift Groq represents is making intelligence faster and cheaper than ever before. If you're building anything in the AI space, understanding this market pivot from training to latency-driven inference is, well, it's essential. Now go explore that new landscape.